Welcome to the eighth session of Basic Mathematical Analysis. In this session, we will be discussing composition of functions. Suppose f is a function from a to b and g is a function from b to c. Then we can define a function from a to c such that the function value under this function is equal to g of f of x. This this is known as composition of G and F, denoted by GOF, G composite F. So it's a function from A to Z. Now here x is in A, and when we apply F to x, we will reach F of x, which is in B. On the set B, we define the function g so that I can apply g on this f of x so that I will get g of f of x. So, if g composite f is defined, then it is a must that this f of x is in the domain of g. Otherwise, we cannot define g composite f. So, g composite f is defined only if uh, f of a, f of capital M, that means range of f is contained in domain of G. So this is an essential condition for G composite f to be defined. So G composite f is defined only if this condition is satisfied. That means range of f is contained in domain of G. Range of f is contained in domain of G. Otherwise, G composite f is not defined. Okay. Now, suppose I can define G composite f as well as f composite G. Means range of f is defined contained in domain of G as well as range of G is contained in domain of f. Both are satisfied, so that we can define f composite G as well as G composite f. G composite f. Then are they equal? Whether f composite G is equal to G composite f may not be. For example, suppose I am taking f of x equal to x square and g of x is equal to 3x. Then what about g composite f of x? It is g of f of x, means g of x square. And if I give input as x, I will get 3 times x as output. So that here I will get 3 times x square. So g composite f of x is equal to 3 times x square. Now what about f composite g of x? This is f of g of x, which is f of 3x, which is equal to 3x square, that is 9x square. So f composite g of x is 3x square. Sorry, g composite f of x is 3x square and f composite g of x is 9x square. They are not equal. So in general, f composite g is not same as g composite f. Okay. Now, suppose f composite g is injective means this function is 1 1. That means f composite g of x is equal to f composite g of y implies x is equal to y. Now, I'm going to prove that if f composite g is injective, g is injective. Let's check. Suppose g of x equal to g of y. If g of x equal to g of y, I can apply f on both sides so that I will get f of g of x is equal to f of g of y. That means f composite g of x is equal to f composite g of y. And here we have f composite g of x equal to f composite g of y implies x is equal to y. So from here we get x is equal to y. So we have started from g of x equal to g of y, and this implies x is equal to y, which means g is an injection. So whenever f composite g is injective, g is also injective. Similarly, you can try whether I will give you one question. F composite G is surjective. Prove that F is surjective. Okay. Now we have one theorem. F is from A to B. G is from B to C. So that we have G composite F from A to C. And taking H as a subset of C, what we have to prove is G composite F inverse of H is equal to F inverse composite G inverse of H. This is what we have to prove. So let's try. Suppose I am taking X in G composite F inverse of H. Then by the definition of inverse image we get G composite F of X is in H. This means G of f of x is in H. And this means f of x is in G inverse of H. This means x is in f inverse of G inverse of H, which is equal to F inverse composite G inverse of H. Conversely, if I take X from F inverse composite G inverse of H, I have X is in F inverse of G inverse of H. And this means f of x is in G inverse of H. This means G of f of x is in H. That means G composite f of x is in H, and this implies x is in G composite f whole inverse of H. So from these two, in the first case we have taken x element of G composite inverse of H, and we got x element of F inverse of, no, not this one, we got um, X element of F inverse composite G inverse of H. Then we took X element of F inverse composite G inverse of H and we got X is in G composite F inverse of H. From these two we can conclude that G composite F inverse of H is same as F inverse composite G inverse of H. Okay. By this theorem, we are concluding the first session of our chapter 1. And in next session of basic mathematical analysis, I will be discussing the topic mathematical induction. So study well, go through the first section. That means videos from session 1 to session 8 carefully, and then we can move on to mathematical induction. All the best.